Hold a hand up near your face for a moment and feel the faint warmth coming off it. That heat is energy leaving your body. The very same energy that lights every star, that fires every thought behind your eyes, that has held your atoms in their places since long before you were born. It is the most ordinary thing there is. You have never, for a single instant of your life, been without it. And it hides something almost embarrassing at its centre. After 400 years of physics, after measuring this stuff to 12 decimal places, after building an entire civilization on our power to push it around, nobody on Earth can tell you what energy actually is. Ask what it is at the base of reality, where the equations are written, and the answer comes apart in your hands. Because the deeper you look, the less energy resembles the solid, sensible quantity you were handed in a classroom. It stops flowing smoothly and starts arriving in indivisible grains that classical physics swears should not exist. The emptiest vacuum we know how to make turns out to be restless, humming with energy that surfaces and vanishes before anyone can catch it. And when we work out how much energy that emptiness ought to hold, our best theory returns a number so wrong it is almost funny. Not 10% off, not 1,000 times off, too large by a factor of 1 followed by something like 120 zeros. That is not a rounding error, that is the universe leaning in and telling us we have misunderstood something close to the floor. So tonight I want to follow a single question as far as it will go. Not the textbook definition, the capacity to do work, which turns out to be a sentence that quietly defines energy in terms of itself. I mean the real question. What is this thing at the bottom? And the honest path toward an answer runs straight through the strangest discoveries physics has ever made, each one insisting that energy is far odder than that tidy conservation law ever let on. And I'll tell you now where this is going, because it's what makes the question worth a whole night. It does not stay out there in the equations. Follow energy far enough down, and it turns into something startlingly close to home. The very stuff your own thoughts are running on as you listen, older than the sun, made before it, on loan to you for a little while, and bound for somewhere after. By the end, what is energy and what are you will turn out to be nearly the same question. But we have to earn that slowly, and it begins somewhere that sounds like it has nothing to do with you at all. Let's start where the trouble started. Long before anyone spoke of quanta, natural philosophers were arguing about something much simpler. What, if anything, stays the same when things move? The 17th century had a real fight about it. Descartes thought the total quantity of motion in the universe was fixed. Leibniz disagreed and put forward a different kind of bookkeeping he called vis viva, living force, which depended not on speed itself, but on the square of speed. That little squared term is easy to read past, but it matters, because it means Leibniz was already circling the thing we now call kinetic energy, a century and a half before anyone had the word for it. The idea only became physics when someone made it bleed numbers. In the 1840s, a Manchester brewer named James Joule built one of the loveliest experiments in the history of science. A falling weight, a set of paddles, a tub of water, and a thermometer he read with something close to obsession. The weight fell, the paddles churned, the water warmed by a hair, and Joule measured that warming again and again and again. What he found was a fixed exchange rate. A given amount of mechanical work always produced the same amount of heat. Always. However he rearranged the apparatus, the ratio held to the decimal. That was the moment it stopped being philosophy. Motion, heat, electricity, light, all these different-looking things could turn into one another, and through every conversion, some running total refused to change. By the middle of the century, it had a name and the authority of law. The first law of thermodynamics. Energy is conserved. In a sealed-off system, the total never moves. You can trade one form for another all day long, but you cannot mint it from nothing, and you cannot make it disappear. It is among the most punishing tests we have ever set for nature, and nature has never once failed it, which is exactly what makes the next sentence uncomfortable. We have a quantity the universe guards without a single exception, and we still cannot say what it is that's being guarded. Hold on to that question. We're going to earn the answer slowly, and it turns out to be stranger and more beautiful than anyone expected. But first, physics had to be broken, twice, and the first break came from something as ordinary as the glow of a hot piece of metal. For most of the 19th century, physicists believed energy was essentially a finished subject. Kinetic, potential, thermal, electromagnetic, all of it obeying conservation, all of it fitting into clean mathematics. Then someone tried to calculate the colour of a glowing object, and the whole edifice cracked. Heat anything up, and it glows. A poker in a fire slides from dull red to orange, to a hot yellow-white as it climbs in temperature. Every object with any warmth at all is quietly radiating light across a spread of wavelengths, and the shape of that spread, how much energy leaves at each wavelength, ought to be something you can predict from first principles. It's about as basic a question as physics can ask. So they asked it. And classical physics answered with nonsense, pure undeniable nonsense. When you work the equations honestly, they predicted that a warm object should pour out an infinite amount of energy at the short wavelength end of the spectrum. Not a large amount, infinite, which would mean that the gentle warmth coming off a stove or off your own skin ought to be a lethal flood of ultraviolet and beyond. It even got a name that captures the embarrassment of it. The ultraviolet catastrophe. Sit with how strange that is. The theory that governed heat, light and motion. The theory that had been right about almost everything. Looked at a warm cup of coffee and insisted it should explode into gamma rays. Your coffee, of course, declines to do this. It sits there and cools. So the equations were not slightly off. They were catastrophically, structurally wrong, and no amount of careful adjustment could rescue them. Something in the foundations was broken, and nobody could see what. The fix, when it came, would be so uncomfortable that the man who found it spent years trying to unfind it. In December of 1900, a serious conservative German physicist named Max Planck stopped the catastrophe. He did it by smuggling an assumption into the mathematics that he himself found almost distasteful. Energy, Planck proposed, does not come in a smooth, pourable stream. It comes in packets, indivisible little units, each carrying an amount of energy set by its frequency. Higher frequency, bigger packet. He called them quanta, and the size of the smallest packet was fixed by a new constant of nature, a number so small nobody had ever needed to notice it before. We call it Planck's constant now, and it is one of the most important numbers in the universe. It is fantastically tiny, which is precisely why, at human scale, you never catch the graininess. You think you're pouring energy like water, when really you're stacking it like coins so small, no eye could ever resolve them. When Planck fed this one assumption into the blackbody problem, the infinities simply evaporated. The high-frequency packets were now so expensive to make that a merely warm object couldn't afford them, so it barely radiated there at all. The catastrophe was gone. The equation matched reality exactly. And here is the human part I find hard to forget. Planck didn't believe it. He thought he'd found a mathematical trick, a bit of scaffolding that made the sum come out right, without describing anything real. For years afterward, he tried to derive the same answer without the quanta, to put the smoothness back. He never could. He had opened a door he did not want to walk through, and the number on the other side did not care what he believed. Energy, at the smallest scale, is grainy. There is a smallest coin. You can hold 1 or 2 or a billion, but never 1.5. And this isn't some fact sealed off in a laboratory. The light falling on you right now is arriving in exactly those indivisible packets. The warmth on your skin is being handed over 1 coin at a time. The graininess Planck couldn't bring himself to believe is in the room with you, is in you, as you rest here. It took a younger, less cautious man to look at that door and walk straight through it. In 1905, Einstein was turning over a puzzle that had been sitting in the corner of physics for 2 decades. The photoelectric effect, shine light on a metal, and electrons come flying off. That much was fine. Light carries energy. Energy frees electrons. The trouble was in the details, and the details refused to behave. Classical wave theory made a very reasonable prediction. Brightness is intensity, and intensity is energy. So a brighter light should hand each escaping electron more energy. Turn the light up, kick the electrons out harder. Simple. Except that is not what the experiments showed. The energy of each electron didn't depend on brightness at all. It depended only on the colour of the light, its frequency. A dim blue light threw electrons out with more energy than a blazing red one. And below a certain frequency, red light produced no electrons whatsoever, no matter how bright you made it. You could leave it on for a year and get nothing. Einstein's explanation was to take Planck's uncomfortable packets more seriously than Planck had. Treat light itself, he said, not as a continuous wave, but as a hail of individual particles, photons, each carrying exactly 1 quantum of energy, set by its frequency. Now the whole thing snaps into sense. 1 photon strikes 1 electron and delivers its fixed little parcel of energy. A blue photon carries more than a red one, so it kicks harder. Turning up the brightness just means more photons per second. More electrons freed, but each one still leaving with the same energy the single photon gave it. And if each red photon is simply too small to free an electron, then a billion of them change nothing. You're just throwing more coins that are each too light to tip the scale. This was deeply awkward, and everyone knew it. Light had been settled science for 100 years, a wave, full stop. Its interference, its diffraction, every classic experiment sang the same note. And now the same light was behaving, unmistakably, like a stream of particles. How can it be both? It can't. Not in any picture your intuition will accept. Light is a wave and a particle, and which face it shows you depends entirely on how you choose to look. That is wave-particle duality, and it isn't a figure of speech or a temporary confusion waiting to be cleared up. It is the actual architecture of the world at small scales. The things down there are not tiny billiard balls, and they are not gentle ripples. They are a third kind of thing our language was never built to hold. And the deeper we go, the more that failure of language turns out to be the whole story. By the 1920s, the strangeness had jumped the fence. If waves of light could act like particles, a young French physicist named Louis de Broglie asked, why shouldn't particles act like waves? He proposed that every electron, every scrap of matter, has a wavelength tied to its motion. It sounded like a student overreaching. Then experimenters fired a beam of electrons at a crystal and watched them come out the other side, arranged in the exact striped pattern of interference. The fingerprint of waves passing through a grating, the same pattern you'd get from light or from ripples on a pond meeting a row of gaps, electrons, the little charged specks everyone pictured as tiny balls, diffracting, spreading out and overlapping with themselves like something poured, not something thrown. So now matter had a wave to it, and energy came in lumps, and the smooth, obedient, clockwork world of classical physics was quietly dissolving into something far less solid. But once you accept that a particle is somehow a wave, an obvious and disturbing question arrives, and it will carry us the rest of the way down. If the electron is a wave, what exactly is doing the waving? The answer took shape through the 1930s and 40s, and it is the moment energy stops being a property that things have and becomes something closer to the fabric things are made from. The framework is called quantum field theory, and it quietly rearranges everything. In this picture, particles are not the fundamental furniture of reality. Fields are. Not fields in the loose poetic sense, precise physical things, one for every kind of particle, each of them spread through the whole of space at once. There is an electron field lying across the entire universe, a photon field, a field for each type of quark. They overlap, they fill the same room you're sitting in, they reach to the edge of the observable cosmos, and they are never anywhere absent. And what you call a particle is a disturbance in one of them. A little knot of energy, a localized excitation, a ripple that holds its shape. An electron is a vibration in the electron field. A photon is a vibration in the electromagnetic field. Everything you thought of as a tiny object, its mass, its charge, its spin, is really a property of the way its field is trembling in one spot. Let that reach where it's pointing. You are not, at bottom, made of particles in the way a wall is made of bricks. You are made of excitations in fields, standing patterns of energy, humming in the electron field and the quark fields, stable enough to hold together for a while and call themselves atoms and molecules and you. The solidity of your hand is fields refusing to overlap. The world is not a collection of things sitting in empty space. It is a set of fields, and space is never truly empty, because the fields are always there, which turns out to be more than a philosophical flourish. It's the doorway to the strangest thing in this entire story. Here is where empty space stops being empty. These fields are never perfectly still. Even in their lowest possible state, no particles, nothing happening, as close to nothing as physics allows, they refuse to lie flat. Quantum mechanics forbids it, through the uncertainty principle. If a field were to sit at exactly zero value and hold exactly still, you would know two things about it: its value and its rate of change, with perfect precision at the same time. And that is precisely what nature will not permit. So the field trembles, always, everywhere. There is a lowest energy a field can have, and it is not zero. We call it 0-point energy, which is almost a joke, because the whole point is that the zero isn't zero. What we casually call the vacuum, the void, empty space, nothing, is in truth a quiet, ceaseless seething. A field at rest that cannot stop moving. You can picture where this comes from without touching the mathematics. Think of a field as an endless collection of springs, one for every possible wavelength, each able to vibrate at its own pitch. Quantum mechanics says a spring can never be brought to a perfect, motionless stop. Even in its calmest state, it keeps a last irreducible shiver, half a quantum of energy it cannot shed. For a single spring, that's nothing, a tremor too small to matter. But a field has springs at every wavelength, without end, crowding closer and closer together as the wavelengths shrink towards zero. Add up that last little shiver across all of them, everywhere in space, and you're no longer talking about a negligible tremor. You're talking about an ocean of energy lying beneath the apparent emptiness of every cubic inch of the cosmos, yours included. The chair you're resting in, the air in the room, the dark between the stars, all of it floats on this hum that can never be switched off. Now you'd be right to be suspicious. This is a bold claim to hang on a piece of mathematics. If empty space is humming with energy, that's the kind of thing you ought to be able to catch in the act, to put on a table and measure. And in 1948, a Dutch physicist named Hendrik Casimir worked out exactly how. Casimir's idea was quietly brilliant. Take two flat uncharged metal plates and bring them very close together in a vacuum. The restless quantum fields fill the space around them, but between the plates, in that narrow gap, only certain wavelengths of the trembling can fit, the way only certain notes will sound on a short guitar string. Outside the plates, every wavelength is allowed, so there is slightly less of this vacuum energy packed between the plates than surrounding them, and that imbalance should press the plates together. A force coming out of nothing at all, out of the structure of empty space itself. For decades it stayed a beautiful thought experiment, too delicate to catch. Then, in 1997, a physicist named Steve Lamoureux, working at the University of Washington, finally pinned it down. He took surfaces polished to near atomic smoothness, suspended them in a vacuum chamber, and brought them to within a few millionths of a meter of each other. And he measured the pull. Not gravity, far too weak at that scale, not static electricity. The surfaces were neutral. A gentle, insistent force drawing them together, arriving on schedule, matching Casimir's prediction. Since then it's been measured again and again, on flat plates and curved ones, on different materials, always agreeing with the theory. So this is not a metaphor, and not a maybe. Empty space has energy, and you can feel it push. The vacuum is doing something, which is a triumph right up until you try to add it all up. Because if the vacuum is full of this energy, a very natural question is, how much? Sum the restless 0-point energy of every field, across every possible wavelength, throughout every cubic centimetre of space. Do that honestly, and you get a number that should stop you cold. When you carry out that sum, using the best theory we have, the energy packed into a single cubic metre of empty space comes out at something like 10 to the power of 113 joules. A 1 with 113 zeros after it, in a cubic metre of nothing. Now go and measure what the vacuum's energy actually is. We can do this, not with plates, but by watching the whole universe. Empty space carries a faint energy that pushes the cosmos to expand, and we can read its value off the sky. It comes out to roughly 10 to the power of -9 joules per cubic metre. A tiny, tiny number. Set the prediction beside the measurement. The theory overshoots reality by something like 120 orders of magnitude. A 1 followed by 120 zeros. This is, without exaggeration, the largest gap between prediction and observation anywhere in science. That's so absurd that physicists gave it a name that sounds almost sheepish. The cosmological constant problem. And I want to be honest with you about its status, because it's tempting to imagine that somewhere there's a clever resolution the popularizers just haven't mentioned. There isn't. It has stood, essentially unmoved, for decades. You might reach for the obvious escape. Maybe all that vacuum energy simply cancels itself out, and the true value is 0? But it can't be 0. We know it isn't, because the Casimir plates really do pull together, and because the real universe really is being pushed apart by exactly this kind of energy. The fluctuations are there. The push is there. It's just that the amount is smaller than the theory says by a margin that beggars belief. People have tried, of course, to explain the gap away, and the attempts are worth knowing, if only to feel how stuck we are. One elegant idea is that nature hides a symmetry that pairs its particles up, so their vacuum contributions come with opposite signs and cancel. One kind of particle adding energy to the vacuum, its partner subtracting just as much. If that pairing were exact, the vacuum energy would fall to 0 on its own. It's a lovely thought. The trouble is that the pairing plainly isn't exact. We've searched for the partner particles it requires and haven't found them. So at best it softens the catastrophe without curing it. Another line of thinking gives up on deriving the number at all and reaches instead for a multiverse. Perhaps there are countless universes, each with its own value of the vacuum energy, and we simply happen to live in one of the rare, quiet ones where the value is small. Because in any universe where it was large, space would have torn itself apart far too fast for galaxies or stars, or anyone, to form. We find it small because we couldn't be here to find it otherwise. Whether that's a genuine insight or a surrender dressed up as one depends on your temperament, and physicists honestly disagree about which. What nobody has is a mechanism, a reason, coming out of the equations themselves, that the number lands where it does. So we have arrived only partway into the night at something remarkable. The more precisely we try to say what energy is in the emptiest possible place, the more clearly the numbers tell us we're missing something enormous. Keep that gap in the back of your mind. It doesn't get resolved tonight. Nobody's resolved it. But everything we look at from here will be lit by it. For now, let's go back inside the atom, because the strangeness isn't only in the vacuum. It's in what energy becomes the moment you try to measure it. In the world you move through, energy is just an amount. So many joules in a battery, so many in a sandwich, a single figure you could in principle write down. Quantum mechanics takes that certainty away in a way that's hard to hold in the mind. Down at the quantum level, energy is bound up with an object the theory calls the Hamiltonian, the piece of mathematics that governs how a system moves from one instant to the next. When you ask a quantum system what its energy is, you don't get to reach in and read a number off a dial. The system has a set of allowed values, and a measurement lands you on one of them. But before you look, and this is the part that never stops being strange, the system need not have a single energy at all. It can sit in a superposition, spread across several possible energies at once, each with its own weight of probability. Not one value you happen not to know yet, several values overlapping until the measurement forces a choice. There's a beautiful and unsettling twist in how that spread behaves. Between measurements, the cloud of possibilities doesn't drift or wander at random. It evolves with perfect clockwork precision, marching forward according to a single equation Erwin Schrödinger wrote down in 1926. Hand it the shape of the possibilities now, and it returns their exact shape a moment later, with the same iron certainty Newton's laws hand a planet. So the strangeness isn't in the evolving, it's in the reading. The equation delivers, with total determinism, a set of probabilities, this energy, with such a chance, that one with another, and then the instant you actually look, the universe reaches into that distribution and draws a single result, and nothing in the equation, nothing anywhere that we've ever found decides which. The odds are laid down like law. The outcome comes up like a card. A universe that computes its own possibilities flawlessly and then rolls dice to choose among them. Einstein hated this. His famous line about God not playing dice was a complaint about precisely this feature. And yet every experiment ever performed insists the dice are real. So even the energy of a single atom is, right up until you measure it, not a fact but a forecast. And every atom in you is, at this level, a haze of maybes that only looks settled because nothing ever catches it mid-decision. Which turns the conservation law we started with into something subtler than the classroom version. Classically, you can point to any instant and say the total energy is exactly this, and it will be exactly this forever. Quantum mechanically, energy is conserved on average. Measure a great many identical systems, and the mean holds rock steady. But an individual measurement can surprise you, and the reason it can It's tied to one more twist of the uncertainty principle. You've probably heard the uncertainty principle stated for position and speed. The more sharply you know one, the blurrier the other. There's a version for energy and time as well. You cannot pin down both the energy of a system and the precise moment you're asking about with unlimited precision at once. Over a very short interval, the energy of a system is fuzzy, not unmeasured, but undecided. And that fuzziness has a famous consequence. Over brief enough stretches of time, the strict energy books can be left open. Physicists talk about virtual particles here, fleeting disturbances that let a force get carried from one particle to another, an electron pushing on another electron, bypassing something between them. It's worth being careful about the language, because the popular version, particles constantly popping into existence out of nowhere and vanishing before they're caught, makes it sound like the vacuum is throwing a party you're not invited to. That image runs ahead of the physics. Virtual particles are, more honestly, a bookkeeping device, terms in a calculation, a way of tallying how the fields nudge one another. They aren't little objects briefly existing. What's real is the field, and its restlessness, and the forces that restlessness produces. But, and this is why the bookkeeping earns its keep, those calculations work. They work to a degree that has no equal anywhere in science. The theory of how light and matter interact predicts one particular property of the electron, the strength of its tiny internal magnetism, and when you measure that property and compare, theory and experiment agree to about 12 decimal places. 12. It's the most precisely tested prediction humanity has ever made, and it only comes out right because the calculation faithfully includes all that restlessness of the fields. So the vacuum's trembling is not a story we tell, it's woven into the single most accurate number in physics. Take a breath here, because we're about to turn the last solid thing to smoke. We've watched energy come apart into grains, then into probabilities, then into something the vacuum lends out and takes back. But through all of it, you could still reach for one thing that feels unarguably solid: the weight of matter, the heft of your own body. Surely that is real stuff, not bookkeeping. Hold on to that certainty for one more moment, because it's the next thing to go. Now for the piece of this everyone half knows and almost everyone slightly misremembers. E equals mc squared. You've seen it on posters and mugs. The usual gloss is that mass can be converted into energy, that under the right violent conditions a bit of matter gets cashed in for a burst of power. That gloss isn't wrong exactly, but it hides the deeper and stranger truth. Mass doesn't convert into energy. Mass is energy. It is one of the forms energy takes. Energy locked into the sheer existence of a thing, standing still. The proton in a hydrogen atom makes the point beautifully. You'd assume its mass is just the mass of the quarks inside it. It isn't, not even close. The quarks themselves contribute almost nothing. Nearly all of a proton's mass is the energy of what's happening inside it. Quarks racing about, the fierce binding energy of the force that holds them, the churn of the fields. Weigh a proton, and you are overwhelmingly weighing motion and binding. You are weighing energy. The c squared in Einstein's equation isn't some cosmic exchange that has to be triggered. It's just a conversion between the units we happen to measure mass and energy in, back before we understood they were the same thing. Once you feel that in your gut, the fireworks make sense. When a particle meets its antiparticle and they annihilate, their mass doesn't vanish into some other stuff. It was energy all along, and it simply changes costume from the localized energy of matter into the streaming energy of light. Run it backwards and the same truth holds. At the great accelerators, where protons are hurled together at nearly the speed of light, The raw energy of the collision congeals into brand new particles that did not exist a moment before. Energy becoming mass, right there in the detector. Matter is just one of the shapes energy can be frozen into. And because mass is energy, and because energy at the quantum level can hang in superposition, you arrive at a conclusion that sounds impossible and isn't. In recent years, physicists have managed to place atoms into quantum superpositions of two different internal energy states. The atom, in a real sense, holding two slightly different energies at once. Since energy is mass, that is also, quietly, a superposition of two slightly different masses. The very heft of a thing, its this muchness, smeared across possibilities until something forces it to settle. The line between energy and mass, between the definite and the undecided, keeps refusing to stay where we draw it. I told you a moment ago that the quarks inside a proton barely weigh anything, that nearly all of a proton's mass is energy, motion, and binding. That's true, and it leaves a loose thread hanging, because the quarks do weigh something, so does the electron. Not much, but not nothing. So where does that little scrap of genuine intrinsic mass come from? The mass a fundamental particle has all on its own, standing alone, with nothing racing around inside it to account for. For a long stretch of the 20th century, this was quietly embarrassing. The most elegant version of particle physics, the one with the most beautiful mathematics, the symmetries that everything else clicked into, only worked if the fundamental particles had no mass at all. Massless. Every one of them flying at the speed of light, unable to slow, unable to settle, unable to bind into so much as a single atom. Exquisite mathematics describing a universe with nothing solid in it. And that is plainly not the universe you're sitting in. Electrons have mass, they circle nuclei, atoms hold their shape. So either the beautiful theory was wrong, or it was missing a piece. The missing piece turned out to be, you can probably guess by now, another field. In the 1960s, several physicists worked it out. The name that stuck to it belongs to Peter Higgs. They proposed one more field, threaded through all of space, with a strange and specific property. Unlike the electron field or the photon field, which lie quietly at zero when nothing is exciting them, this field settles at a value that is not zero, everywhere, even in the deepest vacuum. It is switched on throughout the entire universe, a background you can never turn off, and every particle that moves through space is wading through it. The mechanism, in the plainest words I can manage, is this. Some particles interact strongly with this ever-present field. They're gripped by it, dragged on, made to resist every change in their motion. And resistance to being pushed around is precisely what we mean by mass. Other particles barely feel the field and slip through nearly free, ending up almost massless. The photon ignores it completely, which is exactly why light has no mass and can do nothing but travel at full speed forever. So mass at this depth is not a quantity of material stuffed inside a particle. It's a relationship, a measure of how firmly a particle is held by a field that fills the vacuum. The electron is heavyish because it's gripped. The ghostly neutrino is a wisp because it's barely touched. The light reaching your eyes is massless because nothing holds it at all. Feel how thoroughly that dissolves the old picture of mass as a mount of stuff. There is no stuff. There is a particle, which is a ripple in one field, dragging against a second field that pervades all of empty space. And the strength of that drag is the number we call its mass, which, through E equals mc squared, is simply a form of energy. It is fields, trading influence, all the way down. Mass is one of the tolls charged for the passage. For decades, this was a story with no proof. A beautiful proposal about an invisible field. But if the field was real, then with enough energy you ought to be able to make it ripple, and a ripple in the Higgs field would itself be a particle, the Higgs boson. So we went hunting for the ripple. It took one of the largest machines ever built, the Great Ring at CERN slamming protons together hard enough to shake the field itself. And in 2012, after a search of decades, they caught it. The Higgs boson was real, which meant the field was real, which meant the mechanism was right. The weight of nearly everything you have ever held traces back to how tightly it is gripped by a field, humming in what we once had the nerve to call nothing. And notice how it rhymes with the rest of the night. We keep going down looking for the solid thing at the bottom, the substance, the stuff, and we keep coming back, holding a field, a fluctuation, a relationship. Even mass, the sheer heaviness of the world, the thing that makes a stone in your hand, turns out to be energy caught mid-conversation between fields. The weight of you is a dialogue in the vacuum. Let me tell you my favourite story in all of physics, because it's the cleanest case of the mathematics knowing something before the physicists did, and of energy being far stranger than anyone had ordered. Go back to the late 1920s. Quantum mechanics is young and working, but it has a quarrel with Einstein's relativity. The equation that governs how quantum systems change in time treats time and space as different sorts of things, and relativity insists they be woven together as equals. So the new theory handled slow particles beautifully and came apart for fast ones. Someone needed to write down a quantum mechanics that obeyed relativity from its first line. A quiet, famously sparing Englishman named Paul Dirac did it in 1928. He found an equation that described the electron and honoured relativity at once, a result so clean it ended up carved near his name in Westminster Abbey. But the equation arrived carrying a passenger nobody had asked for. When you solve it, it doesn't only describe electrons with positive energy, it also insists, stubbornly, on solutions with negative energy. Electrons with less than nothing. Now, negative energy is exactly the sort of thing you'd love to dismiss as a mathematical ghost. A spare root, like the negative answer you shrug off when a quadratic hands you two. But Dirac couldn't shrug it off, because in quantum mechanics things don't sit still. An ordinary electron would happily tumble down into those negative energy states, shedding light as it fell, dropping deeper and deeper with no floor to catch it. The stable matter of the world simply shouldn't exist, so the equation was either broken or it was trying to tell him something he didn't yet know how to hear. Dirac trusted the equation, and the reading he finally arrived at was audacious. Those negative energy solutions, he decided, describe a real mirror to ordinary matter. Particles with exactly the electron's mass but the opposite charge. A twin of every particle, identical in weight, reversed in sign. Antimatter? Pure consistency, worked out with a pen, had predicted an entire shadow inventory of the universe, years before anyone glimpsed a single piece of it. Then, in 1932, Carl Anderson was photographing cosmic rays, the particles that sleet down through the atmosphere from space, and he caught one curving the wrong way in his magnet. Same mass as an electron, opposite charge. Precisely the thing Dirac's equation had summoned out of nothing but the demand to be consistent. The anti-electron, the positron. The mirror world was real, and it had been found not by someone scanning the heavens for it, but by someone who took an equation at its word. And this belongs in a story about energy, not off to the side as a good anecdote, for one reason. Antimatter is what you get when you insist that energy obey relativity all the way to the bottom. The deep relationship binding a particle's energy, its momentum, and its mass has two roots, positive and negative, the way the square root of a number has two. And nature, it turns out, spends both. In the field picture we've been building all night, it's cleaner still. A particle and its antiparticle are two excitations of the very same field, mirror ripples in one underlying medium, which is why, when they meet, they can erase each other so utterly. An electron and a positron annihilating, their whole mass unlocking into two flashes of light, energy released from matter, with a completeness nothing else in nature permits. And it runs the other way too. Pour enough energy into empty space, as we do in the violent heart of an accelerator, as the whole universe did in its first instance. And it doesn't merely make particles, it makes them in matched pairs, one particle and one antiparticle together, drawn out of raw energy in perfect balance, because the books must be kept, which sets up a question that still keeps cosmologists awake at night. If energy always makes matter and antimatter in equal measure, and if the two annihilate on contact, then the early universe should have made precisely as much of each, and it should all have cancelled, leaving nothing but a cosmos of light. No stars, no planets, no one here to wonder about it. Yet here you are. Somehow, in those first fractions of a second, for reasons we still cannot fully explain, matter edged out antimatter by roughly 1 part in a billion. Nearly everything annihilated with its twin, the universe flared almost entirely into light, and the faint leftover surplus of matter, that 1 in a billion remainder, is everything there is. Every galaxy, every star, every atom of you is the small change the universe failed to cancel. We are the rounding error in a colossal act of subtraction. And why the subtraction came out slightly uneven is one more thing, on a night full of them, whose consequences we can measure to exquisite precision and whose cause we cannot yet name. We've been circling a question this whole time and quietly refusing to answer it. Why is energy conserved at all? What is it that's being kept constant? The answer is the most beautiful thing in this story, and it comes from a mathematician most people have never heard of. Her name was Emmy Noether. In 1918, working at Göttingen, barred for years from a paid position, because she was a woman, lecturing at times under a male colleague's name, just to be allowed in the room, she proved a theorem that reaches down to the root of physics. It says this: every continuous symmetry of nature corresponds to a conserved quantity. Wherever the laws of physics don't care about some change, something is protected. Follow what that means. If the laws of physics are the same over here as over there, if space has no special place, then momentum is conserved. If the laws don't care which direction you face, if space has no special orientation, then angular momentum is conserved. And if the laws are the same today as they were yesterday and will be tomorrow, if time has no special moment, then energy is conserved. You've actually seen the second of those with your own eyes. A figure skater pulls her arms in and spins faster. She throws them out and slows. Nothing pushes her. She's just cashing in a symmetry. The fact that the laws of physics don't care which way she's oriented, and the conserved quantity that guarantees is the spin we call angular momentum. That everyday pirouette and the conservation of energy are the same kind of fact, cut from the same cloth. One comes from space having no favourite direction, the other from time having no favourite moment. Noether saw that they were all one idea, that behind every quantity nature refuses to let change. There stands a symmetry, some way the universe looks the same after you've altered it. Conservation laws aren't a list of separate rules the cosmos happens to obey. They are the shadows of its symmetries, and energy is the shadow cast by the evenness of time. Read that once more, because it rearranges everything we started with. Energy is conserved because the rules of the universe don't change as time passes. That's the whole reason. Energy is not a fluid, not a substance, not a thing you could ever isolate in a jar. It is the quantity that stays fixed because the laws hold steady, while time flows. It is, quite literally, the shadow that time's evenness casts on the world. The symmetry comes first. The conservation is its consequence. That is the answer to the question we've been carrying since Jules' paddles turned in the water. What is being conserved? A bookkeeping quantity that exists because time treats every moment alike, and it reframes energy as something almost ghostly, not stuff, but the trace of a deep regularity in how the universe is put together. It's a more abstract answer than you wanted, maybe, but it's truer than the capacity to do work, and it opens onto something even stranger. Because if energy conservation is only the shadow of time's evenness, what happens when time stops being even? Now for the part that quietly overturns the sentence they wrote on the board in your classroom. If energy is conserved because the laws don't change with time, then in a universe where the very stage is changing, that guarantee can slip. And our universe is changing. Space itself is stretching, and has been since the beginning. A photon travelling across that expanding space has its wavelength stretched along with it, drifting toward the red, toward lower frequency, which means lower energy. The light of the early universe, once fierce, has cooled over billions of years into a whisper of microwaves barely above absolute zero. So ask the simple question, that energy the photon lost, where did it go? Nowhere. It didn't turn into something else. It didn't pass to another object. On the largest scales in an expanding universe, the total energy is simply not a conserved quantity. The stage is not the same from one age to the next. Time has a preferred direction written into the expansion, and the symmetry that protected energy no longer holds across the whole cosmos. I want to be careful because this gets overstated locally in any patch of space small enough that the expansion doesn't matter. In your room, in the solar system, in a whole galaxy, energy is conserved as faithfully as ever. Your coffee's heat goes into the air, and the mug, and the table, and every joule is accounted for. Nothing is quietly appearing or vanishing on your kitchen counter. But zoom out to the universe entire, and the tidy grand total you were promised as a child doesn't even have a clean meaning. The thing you were told could never be created or destroyed can, on a large enough stage, do both, because energy was never the bedrock. Time's symmetry was, and time's symmetry can break. So if energy can't quite be tallied for the whole universe, and if it drains away as space expands, that reopens an old, childish, excellent question. When your coffee goes cold, when the battery dies, when the star burns out, where does the usefulness go? Because it certainly feels like something is lost. The resolution to that old question is one of the quiet triumphs of physics, and it turns on a distinction we usually blur. Energy and useful energy are not the same thing. When your coffee cools, not one joule goes missing. The heat that was concentrated in the hot liquid spreads out into the air, the mug, the table, until everything drifts to the same lukewarm temperature. The total energy in the room is exactly what it was. What changed is that the energy is now smeared evenly. An evenly smeared energy can't do anything for you. You can't drive a current, or lift a weight, or brew a second cup from a room that's all one temperature. The energy is still there. It has simply lost the unevenness that made it useful. That spreading has a name: entropy, a measure of how thoroughly energy and matter have been shuffled towards sameness, and the second law of thermodynamics says It only ever increases in a closed system. Energy is conserved. Entropy climbs. Heat flows from hot to cold and never spontaneously back. Things mix and never spontaneously unmix. The universe is not running out of energy. It is running out of differences. And differences are what everything interesting is made of. Push that all the way to the end, and you get a bleak and beautiful prediction. If entropy only rises, the far future is a universe smoothed perfectly flat. Every gradient gone, every fire burned out, all the energy present, but spread so evenly that nothing can ever happen again. Physicists call it the heat death, not an explosion, not a collapse, just a warm, featureless, eternal stillness. But we are nowhere near it, and the reason we're not is itself one of the deepest puzzles in the whole of science. The universe is still young enough that stars ignite, galaxies collide, and elaborate patterns like planets and people get built. And that's only possible because the universe began in an extraordinarily ordered, low-entropy state. The Big Bang wasn't just hot, it was smooth almost past belief. Matter and energy laid out with astonishing uniformity. Every ordered thing that has happened since, every star, every living cell, has been the universe slowly cashing in that original, improbable smoothness, sliding downhill toward disorder, and doing gorgeous things on the way down. Why the universe started in so orderly a state, nobody knows. It sits right at the crossroads of energy, entropy, and time, unexplained, waiting. We are, all of us, riding that slope while it lasts. So let's follow the energy in your own body back up the hill, as far as it goes. Right now, as you rest here, your cells are pulling apart small molecules and spending the energy stored in their bonds to hold you together, to fire a neuron, pump an ion, build a protein. You're a pocket of exquisite order, and you pay for it by pouring disorder into your surroundings. Heat off your skin, carbon dioxide from your breath. The books balance. The universe's entropy climbs a little so that yours can stay low a while longer. For as long as you're alive, you are a small stubborn eddy running the other way against the current. And the energy funding all of it traces back, without a break, to the sun. Sunlight lands on a leaf. The leaf locks the energy of those photons into chemical bonds. You eat the plant, or eat something that ate the plant, and you draw that stored sunlight out again. The sun, in turn, is running on the truth we met earlier. That mass is energy. In its core, hydrogen nuclei are crushed together, hard enough to fuse into helium, and the helium that comes out weighs a touch less than the hydrogen that went in. That missing sliver of mass leaves as energy, streaming out as the light that, 8 minutes later, warms your face. The sun is converting its own substance into sunlight, a few million tons of it every second, and has been for billions of years. And the journey of that light is stranger than it sounds. The energy released deep in the core doesn't simply shoot out. It's absorbed and re-emitted, ricocheting through the dense interior for what may be tens of thousands of years before it ever reaches the surface and leaps free. So the sunlight on your skin right now was, in a real sense, made before the first cities and only just got out. Then it crosses the gulf to Earth in 8 minutes flat. There's a quiet vertigo in that, an unbroken chain of energy running from a bit of the sun's own mass, through a slow age of imprisonment, across 93 million miles of vacuum, into a leaf, into your food, into the thought you're having as you listen. Every calorie you've ever burned is starlight that took the long way here. But a star only has so much fuel, and here the story reaches something I find moving. When a large star exhausts the hydrogen in its core, it fuses helium into carbon and oxygen. Heavier stars press on, fusing carbon into heavier elements. still, layer by layer, building the periodic table in their bellies, right up until they reach iron. Iron is the wall. Fusing iron doesn't release energy, it costs energy. So when a massive star's heart turns to iron, the fire that held it up goes out. The core collapses in an instant, and the star tears itself apart in a supernova. And in that catastrophic flash, in the fury of the explosion, the elements heavier than iron are forged. The gold, the silver, the iodine, the uranium, which means something literal and astonishing. The iron in your blood, the calcium in your bones, the iodine your thyroid needs, the gold on your finger. Every atom of it was made inside a star that died before the sun was born. You are, in the most exact sense, built from the ash of dead stars, and the energy binding those atoms together is the same energy that has been in play since the beginning, only redistributed, only wearing a new shape. Nothing was created to make you. Nothing will be destroyed when you're gone. The energy was always here, which raises the largest version of the question we can ask. If energy was always here, where did here come from? Try to total up all the energy in the universe, and something remarkable happens. On one side of the ledger, you have the positive energy, all the matter, all the motion, all the light. On the other side, you have the energy of gravity, which, because gravity pulls things together, counts as negative. And when you tally both columns, they very nearly cancel. As best we can tell, the total energy of the universe might be almost exactly zero. Now follow what that permits. If the grand total is zero, then bringing a universe into being doesn't require any net energy at all. And that has led serious cosmologists, Alan Guth, Alexander Vilenkin among them, to a vertiginous proposal. Perhaps the universe began as a quantum fluctuation, a flicker in the vacuum of the kind we've been discussing all night, ordinarily fated to appear and vanish, borrowing its existence briefly against the uncertainty principle. Except this one didn't vanish. A fraction of a heartbeat after it flickered, a burst of runaway expansion called inflation stretched it out beyond any hope of collapsing back. And the energy that drove that expansion decayed into matter and radiation, into everything, into the particles that became stars and planets and the reader I'm speaking to. A whole cosmos, borrowed from nothing and never paid back because it grew too large, too fast to be called in. We can even reach a little way back toward that beginning and watch energy turn into matter with our own instruments. That same great collider that shook the Higgs field is, in effect, a small time machine. When it drives protons together at nearly light speed, the sheer energy of the impact briefly recreates conditions that last existed a tiny fraction of a second after the Big Bang. And out of that concentrated energy, showers of new particles condense into being, matter crystallizing from motion exactly as Einstein's equation says it must. We are, in those collisions, replaying the universe's opening moments in miniature and confirming the accounting holds. But there's a hard limit to how far back we can push. Even the most powerful machine we could ever plausibly build falls unimaginably short of the energies of the true first instant, and so the very beginning stays out of reach. I have to be honest about what this is. It's a serious idea, not a certainty. We cannot see the first instant. We can see the afterglow of the Big Bang, the microwave light released some 380,000 years in. We can measure the mix of the lightest elements, forged in the first few minutes. We can map how galaxies are strewn across the sky. All of it fits the broad Big Bang picture. But the very first moment is hidden behind an energy so high that no experiment we can build reaches it. And so the question of literal beginning stays, for now, on the far side of a wall we can't yet climb. That wall has a name and an address, and everything we still don't understand about energy seems to live behind it. Before we go through that wall, there's a thread we've left dangling, and it turns out to tie energy to something you'd never expect: information itself. It starts with a puzzle James Clerk Maxwell dreamed up in the 1860s. Imagine a tiny, sharp-eyed demon guarding a little door between two boxes of gas. It watches the molecules fly, and it opens the door only to let fast ones through to the right and slow ones through to the left. Give it time, and it has sorted the gas, hot on one side, cold on the other, a usable difference conjured, apparently, for free. And a usable difference is exactly what the second law says you can't get for nothing. The demon seemed to break the deepest rule we have. For most of a century, the demon sat there, quietly taunting physics. The answer, when it finally came, is gorgeous. The demon has to know which molecules are fast and which are slow. It has to record information. And its memory is finite, so eventually it must erase old records to make room for new ones. In 1961, Rolf Landauer proved that erasing information is not free. Wiping a single bit of memory must release a small, definite amount of heat into the surroundings. The demon's sorting looked like it cheated the books, but the cost was hiding in its mind, in the act of forgetting. Pay the erasure cost and the second law stands untouched. Read that again, because it's one of the most quietly radical statements in physics. Erasing information releases energy. Information is not an abstraction floating above the physical world. It is physical. It has a thermodynamic price, and that binds energy and information together at a level most of us never suspect. The entropy that measures spread out energy is, at bottom, a measure of missing information, of how much about a system we can no longer say. For a long time, this was a theorem on paper, elegant and untested. Then in 2012, physicists finally caught it in the act. They built a system holding a single bit, erased it, and measured the tiny, precise puff of heat that Landauer had predicted more than 50 years earlier. Information has a temperature. Forgetting costs energy. And this isn't some laboratory nicety with no bearing on ordinary life. Every time a computer overwrites a bit, every time a memory's wiped to make room, that same minimum toll comes due, multiplied across the trillions of operations humming inside whatever device you might be holding. A faint and unavoidable warmth that is, in the end, the thermodynamic price of thinking with matter. Your own brain pays a version of it too. Whatever else a thought is, it is also energy being spent and heat being shed, information written and erased in living tissue, obeying the very same law as Maxwell's little demon at his door. And where does this bond show its face most dramatically? At the strangest objects in the cosmos, black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking worked out that a black hole has an entropy, and that its entropy is written not through its volume, but across its surface, the area of its horizon. Every black hole is, in effect, a vast library, and the number of pages it can hold is set by its area, as if the information about everything that ever fell in was stored on the two-dimensional boundary rather than in the three-dimensional interior. Hawking went further and showed that black holes aren't perfectly black at all. The restlessness of the quantum fields right at the edge lets them slowly radiate energy away and evaporate over spans of time that dwarf the current age of the universe. That surface not volume result grew into one of the boldest ideas in modern physics, that the information content of any region of space might be fixed by the area of its boundary, not the space inside it. It hints that energy, information, and the very geometry of space are three views of one thing, and that when we finally understand energy at its root, information will be standing right there beside it. We don't have that final picture. But every time we tug this thread, energy looks less like a substance and more like a relationship, a fact about how things are arranged and how much we can know. There's an obvious objection you might be holding by now. If particles can be in two energies at once, if mass can be smeared across possibilities, if the vacuum is restless with all this quantum strangeness, why does none of it show up in the world you actually live in? Your coffee cup is never in two places. Your body has one definite mass. The everyday looks stubbornly, reassuringly solid. Why? The answer is a process called decoherence, and it's subtler than quantum rules stop at some size. They don't stop. The rules apply to your coffee cup exactly as they apply to an electron. The difference is isolation. A lone particle sealed off from the world can hold its superposition, its several things at once, indefinitely. But nothing large is ever sealed off. A cup is ceaselessly bombarded by air molecules, by photons, by the faint thermal jostle of everything around it, and each of those countless little interactions leaks the superposition out into the environment, spreading it across so many particles, so fast that it becomes impossible to gather back. From the inside, it looks exactly as if the superposition simply collapsed to one definite outcome. For anything as large and as connected as a cup or a person, this happens in a time so short there is no name small enough for it in ordinary speech. So the quantum strangeness never went away. It got diluted into the world too quickly for you to catch. Push hard in the other direction, cool a system to a whisper above absolute zero, wall it off from every disturbance, and the strangeness comes right back. In laboratories, trapped ions and tiny superconducting circuits are held in superpositions of two different energies at once, long enough to be measured and even put to work. That's the beating heart of a quantum computer, energy held undecided across many states at the same time, exploring possibilities in parallel that a definite classical machine would have to plod through one by one. The undecidedness we've been circling all night isn't a philosopher's fancy. Engineers are learning to build with it. There's a question lurking underneath all of this that physics cannot yet settle. When a system is spread across several energies and you finally measure it and get just one, what happened to the others? Some read the mathematics to mean the others were never real, mere terms in an equation, and only the measured value ever counted. Others take the equation at its word and conclude that every outcome happens, each in its own branch of reality, with you split among them, one version reading each result. These pictures make identical predictions for anything you could ever test. They differ only in what they claim is real behind the numbers. I won't pretend to know which is right. Nobody does. But notice that even here, at the disputed root of the theory, energy is the quantity threading through every version. Whatever reality turns out to be, energy is part of its grammar. It would be easy to file all of this under quantum weirdness, fascinating, but remote from anything that matters. I want to push against that, because the graininess of energy, the very thing Planck couldn't stomach, is the reason you exist. Go back to the atom for a moment. An electron bound to a nucleus can't sit at just any energy it likes. It's allowed only a specific ladder of levels, like a guitar string that will sound only certain notes and nothing in between. To move, the electron must absorb or release a photon, carrying exactly the gap between two rungs. Not approximately, exactly. Shine light of slightly the wrong colour on it and nothing happens. The light passes straight through. This is why every element has its own precise set of colours it emits and absorbs, a barcode of light unique to it. The same for that element in your tap water, in the heart of the sun, and in a galaxy 12 billion light years away. And that barcode is the entire reason we can claim to know anything about the distant universe at all. When starlight reaches our telescopes, it arrives stamped with dark lines at exactly the colours its atoms absorbed on the way out, a spectrum we can read like a signature. From those lines we learn what a star is made of, though we will never come within 100 trillion miles of it. We learn how hot it burns, and because motion stretches or squeezes those lines toward the red or the blue, we learn whether it's racing away from us or falling toward us, and how fast, which is exactly how we first discovered the whole universe is expanding. Every fact we possess about what the cosmos is made of, from the sun to the faintest galaxy, was pried loose from the discreteness of atomic energy levels. Planck's reluctant graininess didn't only make matter possible, it became the alphabet the universe spells its ingredients in, and the sole reason we can read them across the dark. Now notice what that discreteness buys. Because the rungs are fixed and sharp, atoms are stable. An electron can't just spiral gently into the nucleus, bleeding off energy smoothly, the way the old classical physics insisted it should. There's no continuous ramp to slide down, only fixed steps, and a floor below which it cannot fall. That floor is why matter lasts. Without the grain, a hydrogen atom would collapse in a flicker. With it, the atoms in your body have held their shape for billions of years. And because those energy levels are exact and repeatable, chemistry is exact and repeatable. The same atoms bond in the same ways every time. So the same amino acids fold into the same proteins in every cell that has ever lived. The reliability of life rests on the fact that energy comes in fixed denominations. Energy, then, isn't only a quantity you tally, it's the thing that decides what can happen at all. Whether a reaction proceeds, whether a molecule holds together, whether a structure is stable or falls apart, all of it is governed by energy landscapes, by which states are reachable, and which are locked away behind a barrier too high to climb at a given temperature. Warmth is just how much energy is on hand to attempt the climb. A diamond is graphite that can't afford the trip. Every stable thing in the universe is stable because the energy to change it isn't available. You are a particular, improbable arrangement that the energy budget of your corner of the cosmos happens, for now, to permit. And the forces holding all of it together are, at the deepest level, just energy being traded. When two electrons push apart, quantum field theory describes it as the electromagnetic field passing influence between them, energy and momentum handed across, and the recoil of that exchange is what we feel as force. Every push and pull in nature, from the light of a star to the grip that holds your atoms in formation, is fields trading energy. The universe, seen this way, is one vast, ceaseless transaction, and energy is the only currency it accepts. For all that, we've been describing a universe we can barely see, and here the master mystery from earlier, that impossible gap in the vacuum's energy, walks back onto the stage wearing its cosmic face. In 1998, two teams of astronomers set out to measure how fast the universe's expansion was slowing down. Gravity pulls. A universe full of matter ought to be gently applying the brakes. They measured distant exploding stars, careful and rigorous, expecting deceleration, and found the opposite. The expansion is speeding up. Something is pushing space apart, and pushing harder as time goes on. The simplest name for that something is exactly what we've been circling all night. An energy woven into empty space itself, a faint pressure of the vacuum driving the cosmos to fly apart faster and faster. We call it dark energy, and it makes up around 68% of everything there is. Then there's dark matter, another 27% or so. We can't see it, but we can feel its gravity everywhere we look. Galaxies spin too fast to hold together On the pull of their visible stars alone, something unseen is gripping them. Light bends around clusters as though far more mass is present than shines. The pattern of the ancient microwave glow only makes sense if this invisible matter was there in the early universe, shaping how everything clumped. We're confident it exists. We simply don't know what it is. Some particle we haven't yet caught, most likely, and experiments are hunting it in deep mines and cold detectors and coming up so far empty-handed. The evidence has been accumulating for the better part of a century. Back in the 1930s, Fritz Zwicky noticed that the galaxies swarming inside a great cluster were moving far too fast to stay bound by the gravity of the matter he could actually see. Something invisible had to be holding them together. Decades later, Vera Rubin measured how stars orbit within spiral galaxies and found the same impossibility, drawn even sharper. The stars way out at the edges circle just as quickly as the ones near the centre, as though each galaxy sat buried in a vast unseen halo of mass stretching far beyond its light. Two entirely different measurements, the same verdict. There is far more gravitating matter out there than there is matter that shines. We have been staring at the gravitational fingerprints of dark matter for 90 years, and we still cannot say whose fingers left them. Add it up, and the arithmetic is humbling. Everything you have ever seen or touched, every star, every planet, every atom of every living thing, is about 5% of the universe's energy. The other 95% is in forms we cannot yet name. We built a magnificent, precise physics on the thin, bright sliver we can reach. And then we looked up and realized it was a sliver. There's an extra needle of strangeness here, one that keeps physicists up at night. Dark energy only recently came to dominate, right around the epoch when galaxies and stars had formed and complex things became possible. Had it dominated much earlier, it would have flung everything apart before galaxies could gather, and there'd be no stars, no planets, no us to notice. That the numbers line up so conveniently right now, in the one era that could contain observers, feels like either a profound clue or an unnerving coincidence, and we can't yet tell which. And the future of everything hangs on which way dark energy leans. If it strengthens, expansion runs away until it tears apart galaxies, then stars, then atoms themselves, a big rip. If it fades, gravity may one day win and draw the whole universe back into a big crunch. If it simply holds steady, the cosmos expands and cools forever toward that quiet heat death we spoke of. We are watching and measuring, and we do not yet know which ending we're living inside. There's one more way energy refuses to be the solid thing you were promised, and it comes from relativity. It turns out that how much energy something has isn't even an absolute fact. It depends on who's asking. Einstein showed that energy and momentum aren't two separate quantities, but two faces of a single object, woven together the way space and time are. And just as two observers, moving relative to each other, will disagree about durations and distances, they'll disagree about energy and momentum too. A particle drifting past you carries a certain energy in your reckoning. To someone flying alongside it, that same particle is at rest and carries less. Neither of you is wrong. Energy is a quantity you read off relative to your own motion, a shadow whose length depends on where the light is coming from. What the two of you will always agree on is a particular combination that stays fixed no matter how anyone is moving. Strip away all the observer dependence and what's left is the particle's mass, its irreducible core, the energy it has just by being in the frame where it sits still. For a photon which can never sit still, that core is zero, which is why light is, in a sense, pure energy and pure motion, the same in every frame, forever unable to rest. And here's a subtlety that turns out to matter enormously. In almost all of physics, only differences in energy have any meaning. The 0 point is arbitrary. You can add a constant to every energy in a system, and nothing observable changes. The energy scale floats freely. It's the gaps that count, except in one place: gravity. In Einstein's gravity, it isn't only mass that bends space-time. All energy does of every kind, including the energy of empty space. And gravity responds to the total, not just the differences. It notices the absolute amount. Do you see what that does? Everywhere else, the vast restless energy of the vacuum could quietly cancel out of the equations, because only differences mattered, and you could set the 0 wherever you liked. But gravity won't let you. Gravity feels the whole of it, which is exactly why that impossible number, the 120 orders of magnitude vacuum energy, becomes a genuine crisis rather than a curiosity. If the vacuum really held that much energy, gravity would feel it, and it would have curled the universe into oblivion long ago, or flung it apart before a single galaxy could form. The fact that the sky is calm and full of stars is telling us, in the loudest possible whisper, that something is cancelling that energy almost, but not quite, perfectly, and nobody knows what. Which is our cue to walk up to the wall at last, the place where the two great theories that have carried us all night stop speaking to each other. Everything I've described leans on two towering frameworks: quantum field theory, which handles the small, particles, fields, the restless vacuum, with that 12 decimal precision, and general relativity, which handles the large, gravity, space-time, the expanding cosmos, with its own flawless record. Each is among the best tested ideas in the history of thought, and they cannot both be the final word, because when you force them into the same room, they refuse to agree. Almost everywhere, you never have to make them talk. Gravity is so absurdly weak on the scale of particles that you can ignore it entirely and get answers of exquisite accuracy. But there is one regime where you can't look away, where something is both unbelievably small and unbelievably dense, so that quantum strangeness and fierce gravity both demand a say at once. The first instant of the universe, the heart of a black hole. The scale where this collision becomes unavoidable is called the Planck scale. Distances and time so tiny they make an atom look like a galaxy. And there, when you try to run the two theories together, the mathematics doesn't just get hard, it breaks, it coughs up infinities, it stops meaning anything, and energy sits right at the fracture. Because energy, as Noether taught us, is defined through time. It's the quantity tied to time's evenness. But in general relativity, time is not a fixed backdrop. It's part of the flexing geometry of space-time. So at the Planck scale, where that geometry itself would be a trembling quantum thing, uncertain, fluctuating, possibly in superposition, what does it even mean for time to flow? And if time doesn't flow in any definite way, what becomes of energy, whose whole identity was pinned to the passage of time? The question doesn't have an answer yet. It might be one of the most important unanswered questions there is. Black holes are where this stops being abstract and starts drawing blood. Take that thread linking energy and information from earlier and push it right to the edge of a black hole, and you get a genuine paradox that has consumed theorists for half a century. Things fall in carrying information, the precise details of whatever they were. The whole slowly radiates its mass back out, the way Hawking showed, and given enough time it evaporates completely. But the radiation leaking away seems to carry no memory of what fell in, which would mean the information is simply gone, erased from reality. And quantum mechanics flatly forbids that. Its equations are built so that information is never truly destroyed, only scrambled. So one of our deepest principles insists the information must survive, and our best description of the black hole says it cannot. Both can't be true. Somewhere in the resolution of that contradiction, many physicists suspect is a real clue to how energy, information, and the geometry of space-time actually fit together, which is why they treat black holes not as exotic curiosities, but as the cleanest laboratory we have for the physics we're still missing. We have candidates. String theory replaces the point-like particle with a tiny vibrating string, and in its picture, every particle is a different note the string can play. Energy, quite literally, as the pitch of a vibration. It's mathematically gorgeous. It naturally includes gravity, and it asks for extra dimensions of space we've never seen and can't currently test. Loop quantum gravity takes the opposite road. It leaves the particles alone and quantizes space-time itself, proposing that space is not a smooth sheet, but a fine weave of discrete units, that there is a smallest possible piece of space, a grain to the world, below which distance stops meaning anything. In that picture, energy might be woven into the geometry itself, curvature and energy becoming hard to tell apart. Both are beautiful. Neither has been tested because reaching the Planck scale directly would take energy so far beyond any machine we could ever build that the gap isn't a matter of engineering but of many orders of magnitude. And there's a third possibility, quieter and stranger than either, gathering support at the edges of the field. That energy and space and time might not be fundamental at all, that they might be emergent, large-scale approximations, the way temperature is a useful idea for a room full of air, but means nothing for a single molecule. In this view, reality at the bottom is something more like a web of quantum relationships, of information and entanglement, and space, time and energy all crystallize out of it when you stand back far enough. If that's right, then asking what energy is made of is a little like asking what a melody is made of. It isn't made of anything. It's a pattern in something more basic. We don't know. That's the honest state of it. But notice where all these roads are pointing, away from energy as a substance, and toward energy as a relationship, a symmetry, a pattern in something deeper. Which brings us, finally, back to the beginning, and to the strangest and simplest answer of all. Before we land, there's a thread worth pulling one more time, because it connects almost everything we've touched, and it runs right through you. Why does time have a direction at all? The strange thing is that the fundamental laws barely notice. Watch two particles collide and film it. Run the film backwards, and the reversed collision obeys the same laws perfectly. Down at the level of single interactions, the universe is nearly indifferent to which way time points, and yet you never watch a shattered cup leap back onto the table and reassemble. You never see cream unswirl from coffee. The future feels utterly unlike the past. Where does that overwhelming one-wayness come from, if not from the laws themselves? It comes from energy spreading out, from entropy. There are so few ways for energy to be gathered and ordered, and so unimaginably many ways for it to be scattered and shared, that a system left alone will almost always drift from the ordered few toward the scattered many. Not because a law forbids the reverse, but because the reverse is so wildly unlikely it effectively never happens. The arrow of time is the arrow of energy dispersing, and it points the way it does, everywhere, for one reason we met earlier. The universe began in that improbable, low entropy, exquisitely ordered state, and it has been spreading out ever since. Every memory you have, every sense that time moves, and the past is fixed, and the future open, is riding on that original order, draining away. You experience time flowing forward because energy is going from concentrated to diffuse. And it's going that way because it started so extraordinarily concentrated. Even your feeling of being carried through your own life is, at bottom, a story about energy and the shape it started in. There's a way to feel how lopsided this really is. Shuffle a deck of cards and you never once worry that you might accidentally shuffle it back into perfect order. Not because sorting is against the rules, but because there is exactly one sorted arrangement and an astronomical number of jumbled ones. So chance carries you overwhelmingly toward the mess. Now remember that a cooling cup of coffee has not 52 parts but something like 1 trillion molecules, each able to hold energy in countless ways, and the imbalance grows so extreme that the heat will spread out and never gather back, stops being a mere tendency, and becomes, for every practical purpose, a certainty. The second law of thermodynamics isn't a stern commandment laid over the world. It's just counting, the crushing weight of the many over the few, played out on a scale so vast the exceptions never once arrive in the whole history of the universe. And that throws the real mystery into hard relief. If disorder is so overwhelmingly the rule, how did the universe ever begin in a state of such staggering order? By this same counting, a smooth low entropy start is absurdly, almost impossibly unlikely. And yet there it was, and everything that has ever happened, including you sitting here now, is the long, slow unwinding of it. Why the beginning was wound so impossibly tight is something we cannot explain. It may be the deepest unanswered question of them all. So energy is bound up with time twice over. Once through Notha, where it's the very quantity that time's evenness protects, and once through entropy, where its spreading is what gives time a direction at all. Take energy out of the picture, and time itself loses both its constancy and its arrow. They are that deeply entangled. There's a famous moment in the lectures Richard Feynman gave to undergraduates, where he stops mid-explanation and says something most physicists would rather not dwell on. It is important to realise, he tells them, that in physics today we have no knowledge of what energy is, not a joke, not false modesty. One of the sharpest minds of the 20th century, at the height of the most successful era physics had ever known, saying plainly, we can write the formulas, we can compute the number, we can watch it stay constant through every transformation. But the thing itself, we cannot say what it is. We have a rule that a certain quantity doesn't change, and we call that quantity energy, and that is very nearly the whole of what we know. I find that honesty clarifying rather than deflating, because it means the question we started with, what is energy, really, was never a naive one to be waved off with a textbook line. It's a question that runs straight to the floor of physics and comes back holding hands with time, with symmetry, with information, with the geometry of space and the fate of the cosmos. And after all of it, we can finally say what the strange answer is. It isn't the answer you'd have wanted at the start, it's better. So, what is energy, really? Every honest thing we can say about it is a face, and no single face is the whole. Energy is what stays constant because the laws of physics don't change from one moment to the next. It's the excitation of quantum fields, the trembling of the vacuum given shape. It's mass standing still. It's Planck's little coin, frequency turned into a fixed packet. It's a quantity two moving observers can disagree about, and a superposition that hasn't decided, and the currency every force in nature is paid in, and the shadow of a symmetry so deep we can only assume it, never explain it. All of those are true. None of them is complete. And the reason they never quite resolve into a single tidy substance is the answer itself. Energy is not a thing. It's a relationship, a pattern, a rule the universe keeps while everything the rule is about keeps changing. You cannot hold it, you cannot photograph it or point to a spot and say, there it is. What you can do is watch it move from sunlight into a leaf, from the leaf into you, from you into the warmth leaving your skin right now, into the air, and eventually, over spans of time too long to feel, into the slow cooling of the whole universe. You are not a container that energy fills. You are a shape it's passing through, a pattern it holds, briefly, on its way to somewhere else. Think for a moment about what's true of you as you rest here. The energy running your thoughts, firing the neurons that are turning these words into meaning, is not new. Trace it back, and it's the sunlight a plant caught. Trace that back, and it's the fusion in the sun's core, mass becoming light. Trace that back, and it's older still, reaching to the first fraction of a second when everything that exists was packed into a single, searing point. The carbon in the breath you just took was forged inside a star that died before the sun was born, and it has carried energy the entire way. Through the wreck of that star, through the cold drift of space, through a planet forming, and an atmosphere gathering, and a body assembling itself around it that happens, for now, to be yours. That energy was never made. It will never be destroyed. It has only ever changed its shape. And you are one of the shapes. And when this particular pattern ends, as every pattern does, the energy won't vanish. It will spread. It will loosen into warmth and motion, disperse into the air and the ground, rejoin the long patient dilution that every ordered thing is quietly part of. The arrangement that is, you will come apart. The energy that moved through it will continue, exactly as it has since the beginning. Indifferent and unbroken, that is the closest thing to permanence this universe offers. Not the pattern, but the continuity beneath it. Not you, but the thread you're briefly a knot in. There's a strange comfort in that, if you let it settle in. Everything's solid about you. The weight of your body, the warmth of your hands, the exact arrangement that makes you this person, and no one else, is on loan. The weight was never stuff. It was the grip of a field in the vacuum. The warmth is atoms jittering, and the jitter is energy that was starlight, and was mass before that, and was a flicker in the first instant before that. Even the matter you're made from is only here because, once in an unimaginable cancellation, 1,000,000,001 particles met 1,000,000,000 antiparticles, and a sliver was left standing. You are, in the most literal sense there is, what didn't cancel. And the thing that carried all of it to this moment, and will carry it onward when you finally loosen your hold on it, is not a substance at all. It's a constancy, the universe keeping faith with its own laws, moment after moment after moment, and we call the running total energy. We measure that thread to 12 decimal places. We build our world on it, and we still cannot say at the very bottom what it is, only that it is the one quantity that holds steady while all else transforms, the trace left by the universe staying true to its own laws as time moves forward. Maybe that's as deep as the question goes. Maybe energy is one of those ideas so woven into the structure of being that asking what it's made of is like asking what existence is made of. And the only honest reply is that it isn't made of anything smaller. It's the grammar reality is written in. For tonight, that's where the question rests. Not solved, held. The universe is still turning it over, still keeping most of its answer behind a wall we haven't learned to climb. In the 95% we can't see, and the first instant we can't reach. But you know something now, that the childhood version of the sentence never told you. Energy can't be created or destroyed, not because it's a substance too tough to break, but because it was never a substance at all. It's the constancy the universe keeps while it changes everything else, including, for a little while, into you. Rest with that. The same steady thread that lit the first stars is the one running quietly through you right now, and it isn't going anywhere. It never has.